Pluto is a remote and confusingly inconspicuous planet that was once a part of our solar system's planetary group. However, later revelations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding disclosure. They suggested that this icy world is on a potential collision course with Neptune. But how could this happen? What might be the repercussions of such a massive event? Are we witnessing a fascinating cosmic anomaly? Or is there more to this impending celestial battle? Join us as we examine the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet partly due to its eccentric orbit, remains a subject of interest and study in the cosmic community. According to recent calculations by leading experts, Pluto's orbit is perilously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have raised the alarm about a potentially catastrophic collision between these two celestial bodies, a collision that could pose a serious threat to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our nearby planetary system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it has not yet completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, veering far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, determined to be 17 degrees to the ecliptic plane. This means that Pluto follows a significantly tilted path compared to the other planets. This inclination and elongated nature add layers of complexity to its orbital arrangement. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune. This challenges what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. Astronomers began evaluating Pluto's orbit soon after its discovery. Initially, they sought to understand its peculiar trajectory compared to planets whose orbits lie relatively close to the ecliptic plane. Pluto's orbit stood out due to its steep inclination and elongated shape. The mystery deepened with the confirmation that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricate design of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's akin to predicting their movements based on their starting positions and gravitational interactions. In Pluto's case, this problem illustrates how the orbits of Neptune and the Sun's gravity all interact in a complicated way. The terms libration and resonance, along with the Kozai mechanism, are key to understanding this phenomenon. Libration, in the specific context of Pluto and Neptune, suggests that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Resonance, on the other hand, refers to the periodic motion of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is perfectly aligned above or below their orbital plane, offering an additional layer of protection from potential collisions. Another critical component of this scenario is the Kozai mechanism, named after three researchers, von Zeipel, Capus, and Lev, who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, influence each other with their gravity. This interplay explains why Pluto's orbit around the Sun is so unusual. Despite its seemingly erratic path, Pluto's orbit has remained stable for billions of years. This suggests that Pluto's journey around the Sun follows a certain order, even if it appears unpredictable at first glance. Predicting cosmic events, especially involving eccentric orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often riddled with uncertainties. While numerical simulations provide a robust method for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models heavily depend on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or deviation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto serves as a reminder that our knowledge of the cosmos remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have significant consequences for the stability and behavior of other celestial bodies within the system. So, why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite these protective forces preventing such an event from occurring, Neil deGrasse Tyson, a prominent astrophysicist, offers a compelling perspective on the mysteries of our planetary system, particularly Pluto's case. Known for his role in reclassifying Pluto as a dwarf planet, Tyson provides insightful commentary on the evolving nature of celestial mechanics. Michio Kaku, another respected physicist and futurist, emphasizes the need for continuous observation and advanced modeling to understand and predict potential cosmic events. He views the interactions between celestial bodies as an important area of study, not just for academic interest but also for practical implications. Kaku's perspective on Pluto and its orbit highlights the necessity of constant vigilance and advanced technology to predict and comprehend the intricate dance of celestial bodies. He emphasizes that events like a potential Pluto-Neptune collision are not mere hypothetical scenarios, but reflect the dynamic and often chaotic nature of space. This underscores the importance of preparing for unforeseen events, both scientifically and technologically. Tyson and Kaku's viewpoints converge on the notion that space is a realm of endless discovery. While our current understanding has grown immensely, it remains incomplete. Both scientists stress the need for ongoing research and the development of cutting-edge modeling techniques to address the complexities of celestial mechanics. The potential interaction between Pluto and Neptune serves as a case study for broader challenges and opportunities in space exploration. It highlights the necessity for rigorous scientific inquiry, innovative technology, and a willingness to adapt our understanding as new data emerges. For both Tyson and Kaku, the mysteries of space, embodied by Pluto's unique orbit, are a clarion call for humanity to continue pushing the boundaries of knowledge. Despite widespread concern, there is a strong scientific consensus that the orbits of Pluto and Neptune will remain stable for the foreseeable future. This is due to their mean motion resonance and the various gravitational forces at play. Therefore, a direct collision between Pluto and Neptune is extremely unlikely. However, the complexities and potential disturbances in orbital elements still make it essential for astronomers to monitor and study these celestial bodies to better understand their long-term behavior. In conclusion, Pluto's orbit, with its eccentricity and inclination, continues to be a source of fascination and scientific intrigue. It challenges our understanding of the solar system and serves as a reminder of the universe's vast, dynamic, and unpredictable nature. The work of astrophysicists like Tyson and Kaku highlights the importance of pursuing knowledge, preparing for the unexpected, and embracing the mysteries of space with curiosity and determination. As we strive to unravel the secrets of the cosmos, Pluto remains a symbol of the endless quest for understanding in the face of the unknown. Any potential dangers they might present, while the chance of a Pluto-Neptune influence is generally speculative and considered far-fetched with current understanding, highlight the significance of constant review and perception. As space science progresses in innovation, including further developed telescopes and computational models, astronomers will refine their simulations and forecasts, ensuring that we stay ahead of the dynamic and ever-changing nature of our nearby planetary framework. Tyson's perspective on Pluto's renaming, alongside Kaku's emphasis on the erratic nature of celestial mechanics, highlights the need for continuous examination and an adaptable understanding of our universe. The potential impact scenario, while emphasizing the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast yet unclear spaces in our understanding of space. Through continued exploration and observation, we strive to unravel these mysteries, ensuring that our knowledge stays aligned with the ever-developing universe. Pluto continues to fascinate scientists and space enthusiasts alike with its distant and enigmatic nature. While its status as a dwarf planet has long been debated, its orbit and unique characteristics continue to engage experts. Recent developments have once again placed Pluto in the spotlight, with the possibility of a gravitational interaction between Pluto and Neptune becoming a focal point of attention in the space community. With Tyson and Kaku bringing this subject to the forefront, the discussion surrounding a potential Pluto-Neptune influence is sure to spark further interest in research. The investigation into these unknown celestial bodies holds the promise of revealing new insights into the mechanics of our solar system. As we peer deeper into space, the dynamic and unpredictable nature of our cosmic neighborhood underscores the need for vigilance and ongoing examination. While the potential interaction between Pluto and Neptune remains a topic of scientific interest, it is crucial to consider the broader context of space exploration and the techniques used to study celestial bodies like Pluto. The discovery of potential risks, such as a hypothetical Pluto-Neptune collision, serves as a stark reminder of the immense complexity and unpredictability inherent in the universe. It highlights the intricate mechanics at play within our solar system, where even the most seemingly stable orbits may harbor hidden vulnerabilities. This notion draws attention to the sophisticated tools and methods astronomers and physicists use to understand the motion of celestial bodies. One significant tool used in such studies is numerical simulations, which allow researchers to predict and model the behavior of planets and dwarf planets over extended periods. By inputting known parameters like mass, velocity, and distance of celestial objects, these simulations can project potential future movements and assess the stability of orbits like Pluto's. Such models often rely on powerful computers and advanced algorithms to handle the vast data and complex calculations required. This approach is particularly important when studying objects with unusual orbits, such as Pluto, whose path around the Sun is highly distinct from other planets in the solar system. Additionally, the role of gravitational interactions between celestial bodies cannot be overstated. For instance, Pluto's orbit crosses Neptune's, and the gravitational pull between these two bodies could theoretically lead to unpredictable outcomes over extremely long timescales. However, due to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship. This gravitational resonance ensures that even when Pluto approaches Neptune's orbit, they never collide. The physics behind this resonance is fascinating, as it demonstrates how the subtle forces of gravity can synchronize the movements of two distant bodies, preventing catastrophic events like a collision. At the same time, many questions remain about how other factors in the solar system might influence Pluto's orbit. For example, the presence of other planets like Jupiter, Saturn, and Uranus could potentially disrupt the delicate balance that keeps Pluto and Neptune in their stable orbits. These giant planets exert their own gravitational forces, which could cause minor shifts in Pluto's trajectory. While these changes are typically minor, over millions or billions of years, they could accumulate and result in more significant alterations. For this reason, astronomers continue to monitor Pluto's orbit closely, looking for signs of any deviations that might indicate a future disruption. Beyond gravitational forces, the influence of the Sun itself also plays a critical role in shaping the orbits of objects in the outer solar system. The Sun's gravity governs the motion of all objects in the solar system, including planets and dwarf planets like Pluto. However, because Pluto is located so far from the Sun's gravitational pull on Pluto is much weaker than on the inner planets, which means Pluto's orbit is more susceptible to external influences. For instance, the Sun's fluctuating energy output over time, such as during solar cycles, could affect the behavior of objects in the Kuiper Belt, where Pluto resides. These subtle changes could impact the long-term stability of Pluto's orbit. Another important consideration in the study of Pluto is its environment. The dwarf planet resides in the Kuiper Belt, a region of space populated with countless small, icy bodies and dwarf planets. The Kuiper Belt is a relatively unexplored frontier, and many of the objects in this region remain poorly understood. As astronomers continue to gather more data from space missions like NASA's New Horizons, which conducted a flyby of Pluto in 2015, we are beginning to gain insights into this distant realm. New Horizons provided remarkable close-up images of Pluto and its moons, revealing a complex world of icy mountains, vast plains, and unusual atmospheric features. This data has opened the door to new questions about the formation and evolution of the outer solar system and how objects like Pluto interact with their surroundings. As scientists continue to refine their understanding of Pluto and its relationship with Neptune, one must also acknowledge the broader implications for space exploration and the potential for future discoveries. The study of distant objects like Pluto helps us gain a better understanding of the history of the solar system as well as the forces that shape planetary bodies. Moreover, these discoveries contribute to our ability to predict the future movements of celestial bodies, which could have practical applications for space missions and the future of human space exploration. With ongoing advances in technology, our ability to monitor and study the outer reaches of the solar system is expanding, opening new frontiers for exploration. While the possibility of a Pluto-Neptune collision is highly unlikely, the fact that such a scenario has captured the imagination of scientists and the public alike demonstrates the continuing allure of the mysteries of space. The complexity of Pluto's orbit, the forces that shape it, and the ways in which it interacts with other objects in the solar system all remind us of the vastness and unpredictability of the universe. As we continue to observe and study these celestial bodies, our understanding of the solar system will expand. The broader significance of exploring celestial mechanics, such as the dynamics of Pluto and Neptune's interaction, extends beyond our immediate understanding of the solar system. It informs us about the universal principles governing the motion of celestial bodies and their potential for influencing each other over time. This knowledge is not only valuable for planetary science, but also critical for preparing humanity for future ventures into space. Understanding gravitational interactions, resonance effects, and orbital stability aids in planning long-term space missions, placing satellites in stable orbits, and even considering colonization or resource utilization of distant celestial bodies. For instance, research on the Kuiper Belt, where Pluto resides, could reveal untapped resources or provide clues about the early solar system's formation. Moreover, such studies contribute to the ongoing debate surrounding the definition of planets, dwarf planets, and other celestial bodies. The controversy over Pluto's status as a planet underscores how scientific classifications evolve with new discoveries. With more missions and advanced observational tools, we may uncover other objects comparable to Pluto or discover entirely new categories of celestial phenomena. The role of missions like New Horizons cannot be overstated. By providing unprecedented data, these missions have transformed Pluto from a faint, distant, to a dynamic world with its own unique characteristics. Future missions might expand on this knowledge by exploring other Kuiper Belt objects, capturing even more detailed observations, or studying Pluto's interactions with its moons and the surrounding space environment. In addition to robotic missions, advancements in telescope technology, such as the James Webb Space Telescope, allow us to observe distant objects with greater precision. These tools help scientists examine the faint signatures of gravitational interactions, trace chemical compositions, and map surface features. These observations provide critical data that feed into simulation models, making predictions about future cosmic events increasingly accurate. The interplay between theoretical modeling and observational data represents the foundation of modern astronomy. As computational power grows, researchers can simulate increasingly complex systems, incorporating a multitude of variables to understand the behavior of celestial bodies. These efforts, in turn, refine our models of solar system evolution and provide a framework for understanding exoplanetary systems. Pluto's unique orbit and its historical interactions with other celestial bodies could also serve as a case study for understanding exoplanetary dynamics. Many exoplanetary systems display unusual orbital arrangements, resonances, and interactions that might echo the complex relationships within our own solar system. By understanding Pluto's behavior, we can apply these principles to distant systems, broadening our understanding of planetary formation and stability in the universe. In summary, the exploration of Pluto, its orbit, and its potential interactions with Neptune is more than just a study of a distant dwarf planet. It is a testament to humanity's curiosity and determination to understand the cosmos. It bridges our knowledge of the past, present, and future of the solar system and inspires the next generation of scientists and explorers to push the boundaries of what we know. As science and technology continue to evolve, so will our ability to unravel the mysteries of distant worlds like Pluto. These efforts promise not only to deepen our understanding of the solar system, but also to open up new opportunities for exploration, discovery, and inspiration.